This unit follows up from the previous units where we were focusing on carbohydrate chemistry. In the earlier units, what we did was looked at in detail the chemistry of monosaccharides, the individual building blocks of carbohydrates. What we're going to discuss here is how we link together those monomeric monosaccharide units to make polymeric sugars, to make carbohydrate molecules. So in getting started on this, what we have to think about is what we are going to do to link two monosaccharides together into a more complex carbohydrate structure. There are some fundamentals that we can think about as we look at this. Later on, we'll be using the structure cellulose as an example, so I have that there on the screen for you. That is taken from the handout that you can find under modules for carbohydrates. Under module one of the handouts is carbohydrates, and you'll find that structure there in case you don't want to redraw it necessarily. So when we are joining monosaccharides together, linking those monosaccharides via covalent bonds, the general theme that we are going to see to link monosaccharides into more complex and biologically useful sugar structures is that they are typically going to be joined by what are referred to as O-glycosidic links. Glycoside refers to sugar, and the link is called an O-glycoside because it's joining two monosaccharides via an oxygen atom. You could also see in some cases an N-glycoside, which is where the sugar molecule itself has a nitrogen atom incorporated into it, and the link to the next sugar unit is via a nitrogen. That occurs in several different antibiotics, such as the aminoglycoside antibiotics that we see in some cases. So linking monosaccharides via these O-glycosidic linkages, what we are going to see is that we're joining two cyclic monosaccharides. And that's typically the theme when we are looking at making these complex carbohydrates, is that we are linking the monocyclic compounds. So we're linking two monocyclic sugars together here in order to form a more complex structure, such as the structure of cellulose, which has a whole long repeat of these linkages between two monosaccharide molecules. So that O-glycosidic link is referring to the fact there's an oxygen bridging the two monosaccharide structures to covalently link those. And what is going to be the case in the general paradigm, and there is a lot of variability with sugar chemistry, but the general paradigm is that what happens is that the glycosidic bond originates at the anomeric hydroxy group of one monosaccharide and then covalently tethers to the carbon atom somewhere in the ring of the next monosaccharide in the chain. So the bond, the glycosidic bond, we describe as originating at the anomeric carbon. Remember that the anomeric carbon is that hemiacetyl carbon, or it could also be an acetyl carbon, depending on the exact structure. So it originates at the anomeric carbon of one sugar, specifically a monosaccharide. And what it's going to do is covalently bond to some carbon atom of the next monosaccharide. And that could be a variety of carbon atoms from that ring. Some of these linkages, many of these linkages, are catalyzed by enzymes that will guide which specific monosaccharide units should join and at what specific position of the ring they should link together. So the way that we describe who links to whom, in other words, which anomeric carbon of the first monosaccharide links to carbon of the second monosaccharide is we refer to the link as a so-called XY link, where X refers to the carbon number of the anomeric carbon. So oftentimes carbon number 1 if we're dealing with a aldose. And the Y value there indicates the carbon number that we're forming a bond to. So let me go ahead and write that down for you. So we refer to the linkage that joins two monosaccharides as being an XY link. And we fill in the X number there with the carbon number of the anomeric carbon. So the carbon that originates as an anomeric carbon, that's the hemiacetyl carbon, carbon number 1 if we're dealing with aldose. And then the carbon number of the carbon that it links to in the second sugar unit, the sugar unit that it joins to, is the carbon number of the carbon that bonds with the anomeric oxygen. So for example, if we take a look at cellulose up top here, we can try to classify that based on the type of linkage that's going on. So if we look at the connectivity between the two structures, the bridge is right here linking those two cycles. That's the connecting point between the two. So in order to determine what the linkage type is, if this is a 1,5 link, a 1,4 link, whatever we're going to describe this XY linkage as, we have to ask ourselves which of the two carbon atoms here, or the one over here, is the anomeric carbon. The anomeric carbon is the one that would have been derived from a hemiacetal. A hemiacetal is a carbon atom that's directly bonded to an ether, such as going around the ring here, and directly bonded to a hydroxy group. And that direct hydroxy group would have originated here, but this oxygen that was originally part of a hydroxy group is now linked over to the carbon. So the carbon atom that I've highlighted in red is the anomeric carbon. You'll notice that the carbon on the other side, the carbon that is linked to, is not an anomeric carbon because this carbon is only directly part of this linkage to the other molecule. It doesn't have an additional link in the ring here to an oxygen atom. So this is not an anomeric carbon. So the anomeric carbon, if we determine which carbon number that would be of the ring, based on the numbering that we learned in the last video or two, that anomeric carbon is at position 1, and then we go around the ring 2, 3, 4, 5. And so starting at position 1 and making our XY linkage, position 1 is where the bond starts because that's the anomeric carbon that has the anomeric oxygen directly bonded to it. That's the oxygen right here that I'm highlighting with my laser pointer. And then we have to ask what carbon number does that connect to, because that's going to be what we fill in as the Y value in this scenario of describing the way that the two structures, the two monosaccharides, have linked together. So in order to come up with the numbering of this second structure, we look for the anomeric carbon within it. And the anomeric carbon is going to be this one in the upper right corner here, because that's the carbon that is directly bonded to the oxygen atom of the ring. And it's also directly bonded to the oxygen atom here that was a hydroxy group, but is now forming a link onward to other monosaccharide units that we're not showing. So position 1 is here. And then we go around the ring in this direction, following the carbons of the ring. So we're going 1, 2, 3, 4, 5. And so you'll notice it is at position 4 where we have that bridge forming to the other ring structure. And so therefore, we refer to this as a 1,4 O-glycosidic linkage because we are joining via an oxygen, hence O-glycoside, the two structures bridging from position 1 at the anomeric carbon, which is listed first here, to whatever position of the second ring we are linking to, and that's going to be position 4 because we number that ring starting at the anomeric carbon and going around following the carbon atoms of the ring. So 1,4 glycosidic linkage is what we are dealing with in cellulose. And cellulose is formed by hundreds or thousands of repeating glucose units that are linked in this 1,4 pattern. So we could keep repeating this pattern over and over again to get the structure of this biomacromolecule. So that is how we would go about doing this. We can also look at another example or type of example that you may run into here as we make this disappear. So an example problem that you might run into, something similar to on an upcoming quiz or on the worksheet as you're practicing these concepts, is something like this. I'm going to tell you that maltose is the 1,4 disaccharide of 2 alpha D glucopyranose units. And you're going to be asked to draw the structure of this. Draw the structure of maltose. And since I've said before, and I will say again, I don't expect you to memorize the structures of the monosaccharides. I'm going to give you the structure of D-glucose here to get things started. So I'll draw this in as our Fisher projection, like we've been doing with our monosaccharide units in the earlier segments. And it's an alpha D-glucose, so keep in mind that means the anomeric hydroxy group is going to be oriented downward because alpha means that it's down at that position that I just drew. And then coming around the ring, the rest of the hydroxy groups and hydrogens are oriented as I'm drawing here. And then we said that maltose is the 1,4 disaccharide of 2 alpha D glucopyranose units. And so it's going to be 2 identical units coming together. So I'm just going to carbon copy what I drew there on the left again to fill in the structure, paying attention that I've got the configuration right at all of the positions of the ring in terms of whether the hydroxy group is oriented up or down, because that does make a difference in the structure and hence in the biological function of these compounds. So linking those two together to form that 1,4 disaccharide, the 1,4 link between the two. What I'm going to do is take the sugar that is on the left, our monosaccharide on the left, and keep in mind that position 1 is that anomeric carbon, the one that's bonded to both an ether group and a hydroxy group. And I am going to utilize the hydroxy group there as my starting point for forming a covalent bond over to position 4, carbon number 4 to be specific, of the receiving molecule. So numbering our second structure here, 1, 2, following the carbon ring around 3, 4, 5. If we're making a 1,4 linkage, what that means is that we need to start here at position 1's hydroxy group, and that's going to form a covalent link over to position 4 there of the receiving molecule. And what has to happen in order for that to occur, I should add, is that the hydroxy group here will end up ultimately leaving as a result of that process, because we can't ever go over the octet rule. So the weakest link there at position 4 is going to break. The weakest link is the carbon-oxygen bond. Carbon-carbon bonds are like rock solid, so those aren't going to break. But the nucleophilic oxygen comes over in this enzyme catalyzed reaction. It's going to attack at position 4 because the enzyme lines it up to do so. And at some point during that mechanism, the leaving group is going to leave. So we will go ahead and draw out the product that results from formation of that linkage. So for my monosaccharide that was originally on the left there, our D-glucopyranose unit on the left. I'm just redrawing the components of that aren't going to change. We can't change any of these aspects of the atoms in the ring because there's no reaction going on at these positions. So there's nothing to allow those to change in stereochemistry or structure. So I've redrawn those exactly like they were. And then we come over to here, and I'm going to highlight this in blue because this is the part that is the main course here of this. And that is our oxygen atom will have come over and formed a bridge to the carbon atom at position 4 of the next chain. And you may be saying, hey, there's an extra proton here. That proton will be lost during a deprotonation step during this enzyme catalyzed mechanism to give just this ether bridge at the end. And then I'm going to go ahead and go in and draw my 6-atom ring of that second glucose unit, and our hydrogen atom still there, still oriented upward. And we can go ahead and draw in the other parts and pieces of this. The other parts and pieces, plugging in all of my atoms in the correct orientation. And in this case, when we get over here to this right-hand terminal, the anomeric carbon of our second unit here, no reaction has occurred at that position of this particular molecule. So the hydrogen will still be oriented up and the hydroxy group still oriented down. It's still going to be an alpha configuration at that position. So let me go ahead and fill that in as alpha with the hydrogen up and hydroxy group down, and that anomeric carbon makes it alpha. And so we have that 1,4 linkage between the two groups, the 1,4 linkage being right here. And we would describe that as an alpha linkage because relative to the anomeric carbon, the oxygen that forms that link is going down, just like if we had an alpha hydroxy group there, that would mean that it was oriented down. So this is an alpha 1,4 glycosidic linkage. That we are forming between those two structures. And this represents the compound known as maltose or milk sugar. So with that, you should be comfortable with taking 2 monosaccharides that I would give you in cyclic form and forming links between them. If I describe the type of link as being a 1,4 linkage, for example, you should be able to show me what the structure of the disaccharide are. There are several different disaccharides, all representing joining 2 identical or 2 different sugar units. So disaccharide means there's 2 units joined together like we have here. We also will commonly run into polysaccharides, and poly generally refers to structures that have 20 or more monosaccharide units. So for example, cellulose has way more than 20 monosaccharide units comprising its structure. And so it's definitely fits in with the theme of a polysaccharide. And much like with proteins, where proteins have elaborate 3-dimensional structures that relate back to the shape of the individual monomeric amino acid units that compose it, polysaccharides can have very specific shapes as well. And they can fold up into elaborate 3-dimensional structures that allow compounds like cellulose to give structural support to celery and other plants. And also, we can think about these providing structural support in the form of things like that. We can also think about them as energy storage repositories. So for example, glycogen is a polysaccharide that is used for the storage of sugars within the body. And some will advocate glycogen loading if you're going to go do intense exercise to build up one's glycogen reserve so that your body has something to metabolize and break down and release sugars as you are doing a long bout of intense exercise. So with that, we conclude our bit on monosaccharides as well as complex carbohydrates, and we'll be applying this information as we go through the semester. So stay tuned for that as we get onward down the road.